Hello, ladies and gentlemen. Firstly, please allow me to introduce myself. This is Liu Horong from KOSTAL Shanghai Management Co. Limited, and I'm a senior Moldflow engineer. I have been working for injection molding industry for more than 10 years. My topic today is the new idea of building Moldflow database in KOSTAL. When you see the title at first sight, you may come up some questions. Why did you set up a Moldflow database? What is database you are talking about here? And how can we use it? To answer these questions, please follow me to go through the report. So let's get started. My report has 6 parts. At first, I will introduce KOSTAL Group and Moldflow procedure in KOSTAL. Next, I will provide a general guide for part design optimization. And then I will emphasize introducing Moldflow database in KOSTAL. Finally, I will share some cases and make a conclusion. KOSTAL Group has 21 subsidiaries and offices around the world. KOSTAL Asia distributes 4 countries: China, South Korea, Japan, and India. And the headquarters of KOSTAL Asia is in Shanghai, China. Since KOSTAL Huayang created in 1995, until now, there are 9 branches, and the employees are more than 4,000. The sales of last year is about 907 million euros. Next, our department. Single part engineering center. Our business include automotive electrical appliances, automobile connectors, and industrial electronics. CT, our department, is single part concept, and we have 3 groups: Moldflow, CT analysis, and tool concept. Here I want to emphasize introducing CT analysis, because CT analysis plays an important role in building Moldflow database. We can see the actual status from CT analysis and make a comparison with simulation results. So I can get a lot of information from the process. And we formed a closed loop among 3 groups. Next, let me introduce Moldflow procedure in KOSTAL. In part design and tool design stage, we did the same work as most companies. For example, runner system and cooling system optimization, and define gate location, and part design optimization. The difference is we will redo Moldflow according to the actual tool layout when the tool design is finished, and put the processing parameters to tool trial department. And when the tool trial finished, they will provide samples to CT analysis. After CT analysis, we can find the best processing parameters and feedback to Moldflow. According to the procedure, we can collect a lot of data. After data analysis, we can build a database. Meanwhile, database can provide a guideline for new part development. So the procedure is a closed loop system. We mentioned database before, and what was database? In my opinion, database is a system, and we should find out the relationship between X and Y. X are some factors, and Y is part quality. And how to build database? It's necessary to follow these steps. At first, we should have a general guide for part design optimization. And then we should identify part CTQ, critical to quality. And then we also need to evaluate the accuracy of simulation. If the simulation results is accurate, we can collect data and data analysis to find the key factors. After validation, we can finally find the relationship between factors and part quality. Now let's go over the details for each step. We have general guide for part design optimization. At first, we should clearly understand the basic shrinkage principle, and then based on the features of our products, we simplified to some typical structures. They are L-shape, U-shape, H-shape, and the ring shape. We researched the warpage trend and found out the root cause and improvement measures for each one. And they can explain most of our products. Next, I will use an example to share how to build a Moldflow database. This is a steering column module, and state housing is a bottleneck in development of SRC. So it's necessary to make a database for state housing. As we mentioned before, we should identify the CTQ. We got the information from our part designer. State housing is a carrier of clock screen or rollers, and the flatness should be less than 0.3 millimeter. So the CTQ of state housing is the flatness. Next, we should find typical structures to represent state housing's behavior. Obviously, state housing is the typical ring shape. According to the warpage status of state housing as ring typical, we know the wall thickness is the most important factor for part warpage. So we made an agreement with our part designer. That is, the difference of wall thickness should be less than 0.2 millimeter. Next, we should choose a correct mesh type and shrinkage model. After validation with actual status, we found option 3 is basically consistent with actual status. So we simulate state housing with 3D mesh and generic shrinkage model. Next, we should consider some constraints in actual process. According to the feedback from our factory, injection pressure is a constraint for state housing. The peak pressure should be less than 180 megbar, and the packing pressure should be less than 60 megbar. Otherwise, some scratch and sunk mark would be happen on part surface. As you know, the injection pressure from simulation is different from reality due to some objective factors. So we have to correct the injection pressure from simulation to identify with the actual status. And we have two methods. Method 1, we try to find out a ratio between simulation and the reality. We collect some data and do data analysis. We found the ratio is related to nozzle diameter. So if we fixed the nozzle diameter, we can find the ratio is 1.52 for state housing. In other words, the collection coefficient is different from nozzle side, material, even part structure. Method 2, we considered from the perspective of solver. We plan to find a way from solver by adjusting some coefficient. So we checked the viscosity model, and we want to adjust D1 from the equation, a formula. There are two reasons. First, D1 is a linear relation to initial viscosity, and D1 is also a data fitted coefficient. And then we simulated many times, setting D1 with different values. And we can find the regression equation between injection pressure and D1. Next, we know the actual pressure in actual process. Based on the actual pressure and the regression equation, we can work out D1 easily. On the other hand, we have to check whether other important simulation items changed or not when D1 set in different values. From the table, we can see the simulation results are same when the D1 value is different. So this method is also feasible. After data analysis, we can find the average D1 is 2.57. So far, we know the constraints in actual process and how to collect it. So now we can provide processing parameter recommendation to actual process. We optimize the packing pressure with profile and the channel's temperature. There are 3 processing conditions to be evaluated in actual process. As you can see, condition 3 is the best. And condition 3 is from the recommendation of Moldflow. So the processing recommendation with Moldflow is effective for state housing. Next, we should find out the key factors to part quality. We also collect some cases, and the processing parameters is recommended from Moldflow. The factors include part size or thickness, gate number, gate location, and injection pressure. For gate location, we summarized 2 types, different site and same site, whenever how many gates there are. And we also have a standard score system to evaluate part quality. After data analysis, we can see part size or thickness, gate type, and injection pressure are key factors. Next, in order to find out the relationship between factors and part quality, we made an agreement scheme. We chose some typical structure of state housing with different wall thickness and different gate type and make a cross-validation. We put the factors and the levels into DOE design and generate a work list. We did simulation according to the order and get the results we need: injection pressure and part quality. From DOE analysis, we can see the p-values are less than 0.05. So the 3 factors are close in relation to the part quality, and no interaction among them. From the plot, we can see the injection pressure is also have a close relation to part quality. So in order to get better part quality from the May effect plot, the wall thickness should be greater than 1.3 millimeter, and part size should be less than 135 millimeter. Injection pressure should be less than 130 megbar. Next, with regression analysis, we can find the relationship between factors and part quality. We just need to input part size or thickness and gate type. We can estimate the injection pressure and part quality, just like the video. We just need to put the part size or thickness and gate type. We can estimate the part quality easily according to the regression equation. This is our database for state housing. Now, let me share some cases how to use the database. This is a software tool from our supplier, and they need us for technical support. From the database, we can see the part quality is not good. And we made a simulation with the process parameters they provide. As you can see, the workpage status is same to actual status. And then we optimize the processing conditions, and the workpage improved by 60 megabar, 60%. But the workpage still can't meet the tolerance. So we have to find a better way for hard tool. From the database, we can see if we change the git tab from same set to different sets, the part quality can be improved a lot. So we changed the gate location from same set to different set, and the workpage status is good in hard tool. And the workpage status can meet the tolerance. Case 2. From the database, we can see the part quality is good, but in actual, the workpage is not good and update with simulation results. To find out the root cause, we went to manufacturing, and we saw the part was separated from core side before injecting. It means that the release force from cavity side is too high. In order to improve the problem, we add some injectors in cavity side. After that, the workpage is bad and is consistent with simulation results. Case 3 is a successful case in trial T1. From the database, we can see the part quality is good. So we provide processing recommendation to actual process. After trial, we can see most of dimensions are within the tolerance, including workpage status. So this is a successful case in trial T1. Now, this is a summary. We have built database for 5 types of parts. As you can see, the key factors are different from each type of parts. Benefits. The benefits is in form of trial times and development cycle. In a word, we cost down about 1,600,000 RMB every year. A future plan. Of course, we want to make more and more database. Now we are building database for livers. And in future, we want to do that for bezel and housing. Finally, give a conclusion. With Moldflow Database, we can evaluate part quality before running simulation in part design stage. If we find the part quality is bad in part stage, we can require part design to optimize the part structure, and we don't need to do Moldflow simulation at the moment. And then we can define gate location quickly and reduce simulation times. We also can reduce trial time based on database and process recommendation with Moldflow. Next, just like I mentioned before, we can reduce the trial times and the developing cycle time. We also have some restricted conditions. It's just suitable for similar serious parts, but not for single or extremely variable parts. And we have to spend a lot of time on data collection and data analysis. That's it. Thanks for your attention.